Bismillah ar-Rahman ar-Rahim. In the name of Allah, the most gracious, the most merciful. Hello everyone, my name is Mawahib Kabbara. I am a telecommunications consultant providing consulting services to telecom operators and service providers in the Middle East in various areas of information technologies, telecom, and AI. In this presentation, I will cover the most important concepts used in neural network training. I'll make sure to explain those concepts clearly, including the math theorems behind them. The agenda for the presentation includes model training, datasets, examples, features, and labels, the types of training, the supervised and unsupervised training, the forward propagation, the linear transformation, the nonlinear activation functions, such as the sigmoid function and rectified linear function, approximation by step functions and how we can approximate any function by a series of step functions, and how the universal approximation theorem builds on the approximation by step function to approximate any function and relationship between the input and the output. We will also cover the inference errors, the loss functions, and we'll do a quick math review of linear equation and how to calculate the slope and how the slope is used in the gradient descent. We will cover the derivatives and chain rule, and then we will explain the back propagation and how it is used to fine-tune the weights and the bias, and how we calculate the gradients to optimize the system prediction. In this video, I will explain how models are trained, the dataset taxonomy, what is a batch, what is an epoch, supervised training, unsupervised training, regression, classification. I will also review the linear equation, slope of a line, derivative of a function, tangent on the error hyperbola, show examples, and then explain inference errors, gradient. Finally, I will explain the front propagation as well as the backward propagation and how to use the chain rule, especially in the backward propagation, and how it is used to tune the parameters recursively until the errors are minimized. If you are familiar with the table data construct made up of rows and columns, then it will be easy for you to understand what we will cover in this slide and in the next slide. A training data set is like a data table made up of rows and columns. Each row in the table is called an example. It contains a set of input values called features and output values called labels. The columns represent the values of the features and labels for all the rows or examples in the dataset. To train a model, we basically feed into it a set of features and label values, and we let the model predict the output based on the set of features provided. Then we compare this predicted output value to the actual label value in the example we are using for training the model. An error value is calculated by identifying the value difference between the predicted output and the actual label in the example. When the examples contain both features and labels, we call this a supervised learning. And in this case, each row of features and labels is called a labeled example. Shortly, we will discuss unsupervised learning as well in the next few slides. Models training is a science of its own. We don't just feed all the data into the model in one shot and expect it to train. It doesn't work like that. A successfully trained model is a model that has its parameters, weights, and biases fine-tuned in a way such that the errors between the predicted values and the labels are negligible or at best zero. Tuning these model parameters require a lot of training iterations, error calculations, back propagation, retuning the parameters, and trying again and again and again. We can't use the same labeled examples over and over to tune these parameters. Otherwise, the model would be overfitted on this dataset. Instead, we must feed different labeled examples at different times and keep fine-tuning the parameters until the model prediction accuracy is optimized. We break down the large dataset into batches, and we feed one batch at a time into the model for training. For example, a 100,000 examples dataset can be broken down into 10 batches, where each batch contains 10,000 examples. During each batch processing, output values are predicted in the forward pass, the error or losses are calculated, then backpropagation process is used to compute the gradient, to tune the parameters, weights and biases, to iterate the process all over again in an effort to optimize accuracy throughout error minimization. For the 100,000 labeled examples, where a batch contains 10,000 labeled examples, it takes 10 batches to complete one full pass of the entire dataset. We call this one an epoch of 10 batches. There are two types of training used for models training, namely supervised learning and unsupervised learning. In the supervised learning, we provide both the features, like the input, and the labels, or the output, in the form of labeled examples. So if we take a look at any example, we see the features, x1, x2, all the way to xn, and we also see the label provided in the same example. We use labeled examples to train the model, and we call this training. Once we train the model with labeled examples, we use unlabeled examples where the label is not provided, and we ask the model to predict the values for the output. This is called unsupervised learning. In this type of training, we provide only the features without the labels in the form of unlabeled examples, so we can see the features x1, x2, all the way to xn, and we don't see the labels because we are expecting the model to predict the output. This is called inference, and it is the model here that is conducting the inference operation. Models can be either regression models or classification models, depending on what these models are predicting. A regression model predicts continuous values, which are varying data values measured over a period of time interval. For example, a regression model would predict the value of a house in California, for example, based on the number of rooms, the area, the zip code, neighborhood, etc., etc. Or the regression model can predict something like, what is the probability that a user will click on this ad? So what the model is predicting is a continuous value. In contrast, a classification model predicts discrete values that include whole concrete numbers with specific and fixed data values determined by counting or classifying output. For example, a classification model would predict whether a given email message is a spam or not spam. The classification model can predict whether the image it's looking at, whether it's the image of a dog or a cat or a hamster. Let us explain the forward propagation in neural network. For simplicity, let us illustrate how neural networks perform the forward propagation. Let's analyze a simple neural network comprising an input layer and an output layer. We're keeping this simple, only one input layer and one output layer. And let us use a diagram on this slide for this purpose. The slide shows two neurons, J1 and J2, at the input layer, shown in orange color, and two neurons at the output layer that we call O1 and O2, and they are shown in green color. In the forward propagation path moving from left to right, a linear transformation operation is performed at every neuron input. So here in this case, X1 and X2 are subject to a linear transformation operation, whereby X1 gets multiplied by a weight W1. Similarly, X2 is multiplied by a weight W2. Then a bias B1 is added to the sum of W1 X1 plus W2 X2. This summation of these linear transformation operations is represented by the variable Z1, which is now the input to neuron J1. The sum of the two linear transformations of the input and their summation at every neuron precedes the activation function that the neuron will execute. This activation function can be, for example, a sigmoid function or a rectified linear function. The neuron can now execute the activation function. The result of the activation function is now the output that we call out J1, generated by the neuron J1. X1 and X2 feeding into neuron J2 are similarly subject to linear transformation with different weights, W3, W4, and a bias B2. Then the sum goes through the activation function in neuron J2. And we call the output of J2 here in this case out J2. Both out J1 and out J2 are now input for the output layer. And they both are also subject to yet another linear transformation first. And we represent below Z3 and Z4 to be the input into the green neurons, so NO1, which is equal to W5 times the output from J1 plus W6 times the output from J2 plus bias B3. Similarly for Z4, the same concept. Now the activation functions we mentioned, they can be a sigmoid function, for example. They can be a rectified linear function. So we see the mathematical equation, 1 over 1 plus e to the minus INO 1 or INO 2. So in short, the neural network performs linear transformation at every neuron input layer, followed by an activation function by each neuron. This applies to the input neuron J1, J2, and by the output neurons O1 and O2. This was an explanation of the forward propagation. We will explain backward propagation later in the presentation in another slide. Let's discuss why linear transformations and activation functions are used in neural networks. Most neural network videos on the internet describe neural networks at a high level only and do not get into the mathematical theories empowering neural networks. In this video series, we do not fly by the concepts. Instead, we try to describe everything to make sure the audience walk away with a solid understanding of how things work in a neural network and why. Neural networks predict outputs through approximation and probabilities. Since the relationship between the input and the output is a function of some sort, can be linear, nonlinear, continuous, discrete, etc., it is important that the neural network model can approximate this relationship through a series of linear transformation by tuning weights, biases, and through using multiple activation functions as well. Mathematically, any continuous function can be approximated as closely as desired by a staircase lookalike function, which is a sum of flat horizontal segments at different heights, which are step functions. The graph in the right-hand side corner below depicts how the target function represented by the green curve is being approximated by a series of step functions or segments in brown colors. The first step function creates the first segment or the first horizontal line, while the second step function that follows can either raise this line if the second step function is positive, or it can lower the line if the second step function is negative. At any point, the approximated graph is a summation of all the previous step functions. What we end up with is a consecutive set of segments or horizontal lines looking like a staircase approximation, trying to approximate the target function. While the linear transformation Wx plus b multiplies x by a weight, thus raising or lowering the value of fx on the y-axis, the bias b can also shift the entire segment, the entire line, upward or downward too. So why does this matter in a neural network? Remember that the activation function can be a sigmoid neuron, for example. So here we're referring to sigma wx plus b. So wx plus b is the input into the activation function sigma. The sigmoid neuron normally produces a smooth S curve as seen in the lower left-hand corner of the screen. If the weight W is made very large, the transition region compresses it into an almost vertical jump. So it jumps directly into 1. In the limit, sigma wx plus b becomes a step function, while the bias b controlling where the jump occurs. In the previous slide, we explained the approximation of a function by a series of step functions. The universal approximation theorem builds on that, and it is used in the neural network. It's one of the major concepts behind neural networks. So a neural network function f hat x can be described mathematically as a composition of linear transformation and activation functions, just like we explained in the previous slide. So for a network with a single hidden layer, shown here in orange color, neurons, the output color shown in blue is given by a mathematical formula here. So Ci is the weight, or the weights actually, applied to the outputs coming from the hidden layer neurons, while the weights, Wi and Bi, are the respective weights and biases applied at the various neurons at the hidden layer. Sigma is the activation function used in the hidden layer at the various neurons. So the idea is that by adjusting the weights, Ci, Wi, and Bi, the bias, the neural network can approximate any continuous function fx over a given domain. Continuing with the universal approximation theorem, so a network with one hidden layer shown in yellow here, or orange rather. So this hidden layer of sigmoid units can get arbitrarily close to any continuous function under certain conditions. A feed-forward or forward propagation neural network with an activation function sigma can mimic the behavior of a step function. For example, by carefully tuning the weights and the biases of the neurons, we can construct a neural network that behaves like a piecewise constant function or a staircase function. Mathematically, this is expressed by the formula f hat x, which we just explained in the previous slide. So let's take a look at the terms here. The sigma WIT, this is the transpose matrix of WI, which is the set of weights applied at the input, multiplying x, plus the bias BI, the various biases applied to the various neurons in the hidden layer, and then processed by the activation function sigma. This term represents the bump or the step in the approximation process. The sum of these terms create the overall approximation of the function. If this is confusing, please go back to the previous 2 slides and take a look again at the approximation through a series of step functions. Let us do a quick review and expand the number of layers of the neural network. So we already discussed that a neural network layer is doing basically a linear transformation on its input, and then an activation function, which is most of the time non-linear warp, and then another linear transformation feeding into the following layer, which will perform another activation function in the form of a non-linear warp, such as a sigmoid function or rectified linear function. The equation, the linear equation, y equal wx plus b, it's the operation of the linear transformation that a single neuron or a single layer performs on its input. It's a building block. It is not claiming a linear relationship between the input and the output at all. So let's take a look at the diagram on the slide. We moving from left to right, we have two inputs, x1 and x2. And there is a set of weights applied to x1 and x2 as they feed into the 4 activation functions in the first layer. Then the output from the activation functions, before they hit the hidden layer, there is another linear transformation function or linear transformation occurring on those output before they hit the activation function at the hidden layer. The output from the hidden layer go through yet one more linear transformation before they hit the activation function at the output layer, and finally the output is generated. So here we extended the 2 layers we discussed in the previous slides into 3 layers here to reinforce the concept of linear transformation plus activation function, which is a non-linear operation. So once we interleave the linear transformation with non-linear activation, the neural network can approximate arbitrarily complex nonlinear functions, which is the substance of the universal approximation theorem. So we talked about the model forward propagation and how we obtained an output. Let's call this output y hat, represented by y with a hat on top of it. This output at the start of the training will not be equal to the actual label we are providing as part of the training examples. In fact, there is some kind of an error between the output value and the label value. Let's take a look at the top left graph, where the line y represents the actual label values, while the orange dots represent the output that the model generated as a result of the forward propagation linear transformation operations and activation functions. The distance between each orange dot and the line y represents the error that the model has produced. In order to observe this error more clearly and to understand how inaccurate the model is, we calculate the square value of this difference between the label and the output. This will amplify the error so that we can observe its impact more clearly. This is depicted in the diagram on the right. Now, if we take a look at the diagram at the bottom of the slide, we can see how the error and loss are calculated for one batch and in the forward propagation only. The diagram, we're not showing the back propagation yet. Let's keep this thing simple for forward propagation only. So for the whole data set, as we mentioned, a data set contains multiple batches, and as we run all these batches sequentially until we process the entire data set D, we produce losses that we add together into something called mean square error, MSE, which is the average sum of all the losses for all the samples divided by n. And it's depicted in the formula MSE equal 1 over n with a summation of the actual label y minus the prediction x squared. So the mean square error, MSE, is the function that specifies the average sum of the losses between the predicted output and the example label values. And this function is an equation of second degree, likely a parabola, because it's an equation of the second degree. So the loss equal the difference between the training label minus the predicted value to the power 2. Okay? Now, when we plot a second degree equation on the xy axis, we obtain something like a parabola. And this parabola represents the MSE function or the loss function, where the loss is actually a function of the weights and the biases. In other words, when we modify the weights, when we modify the biases in the neural network, the curve, the parabola that we see on the screen, okay, it will still be there, but as the weights vary we can see that the dots can move downward toward the minimum or can go upward away from the minimum. So in other words, there are certain values of weights and biases that will help the system to converge where the error or the losses becomes zero or near zero, while there are other values of weights and biases which can make the model diverge away from the minimum loss and the minimum error. So the trick here is to observe how, when we vary the weights and the biases, whether we are moving toward minimizing the losses or whether we are increasing the losses. Now, how fast we move down this curve or how slow down we move down this curve, okay, we will discuss in separate slides in details. So the gradient is the derivative of the loss function. The loss function is an equation of a second degree. Its derivative, it's a line. Now, it's very easy to understand mathematically how to calculate the derivative of an equation of second degree. But it's also as important to understand semantically what a derivative is. The derivative tells us how a function is changing right now at a single point. Geometrically, it is the slope of the tangent to the curve at that point. So, the derivative measures how fast a function's output changes for an infinitely small change in x, which is the input. So, if we look at the formula, f prime x, which is the derivative, it's the limit as h goes to 0 for the function fx of h, meaning the function as x increases or decreases by a small modification, which is h, minus the previous position of x divided by h, which is very, very small. So if the derivative is equal to 0, then the function is momentarily flat, possibly peak or value, meaning it reached the minimum. It's parallel to the x-axis. Now, there is also a second derivative, f double prime x. This second derivative, f double prime x, it shows the curvature of the parabola, whether it's pointing upward, meaning it's concave, or it's pointing downward, which is concave down. We just stated that the gradient is the tangent to the loss function at a certain point, correct? So, because it is also a derivative of the loss function, which is a line, it is important to understand the line equation. So here, this is a math slide, but it helps us to understand the line equation. We see the line equation y equal mx plus b, where b is the intersect of the line with the y-axis. If x is 0, then y is equal to b. M is the slope of the line. It tells us whether the line is shooting upward or downward. And we determine the angle with the x-axis with the formula angle equal the arctangent of m. So for example, if the slope is equal to 2, then the arctangent of 2 is equal to 63.4 degrees. We can also calculate the slope between 2 points for the line crossing 2 points as y2 minus 1 over x2 minus x1, where x1, y1, and x2, y2 are the parameters on the xy axis. So the tangent is equal to the rise divided by the run, and the angle alpha of the line is the arctangent of m. It's very important to understand the line equation and the slope, because this will help us to understand the gradient and how the gradient is moving, whether it's descending or whether it is ascending with respect to the loss function. Now we will introduce the gradient, which is a math function used in statistics. The gradient tells us how much each weight should change and in which direction to reduce the loss. We talked about this in the previous slide. A positive gradient, okay, leads to increasing the weight, which in turn will increase the loss. This is obviously not helpful. And what we need to do in this case is we should move in the opposite direction. We should decrease the weight. A negative gradient, on the other hand, if we increase the weight, decreases the loss. So in this case, we should increase W to decrease the loss faster. The gradient is called here in this case a gradient descent because we prefer a negative gradient over a positive gradient. That's why we call it a gradient descent. We are descending toward the minimum loss. And in the gradient descent, the weights are updated in a process called backpropagation, where certain values are subtracted from the old value to fine-tune it. It's given by the formula: the new weight is equal to the old weight minus eta times the variation of the loss with respect to the weight. The parameter eta directly scales the gradient. So let's take a look at the graph. We see the parabola on the graph. In the y-axis, we see the losses. In the x-axis, we see the parameters such as the weight or the bias, etc. And then we see 3 dots. Now, let's say we are moving from left to right. So when we start with the dot at the top of the parabola, this is obviously the furthest away from the minimum loss, okay? And as we increase the parameter in this case, okay, negatively, we are descending slowly to the second dot, which is closer to the minimum loss. Now, if we overshoot, if we change the weight in the opposite direction, we will overshoot the minimum and then depart away from the minimum loss, which means we are screwing the model. So instead of helping the model to converge, we are causing the model to diverge. So what is the gradient? The gradient at a point on the parabola, on the loss graph, is the derivative of the loss function at that point with respect to the parameter like the weight or the bias. Remember, the parabola is an equation of the second degree. The derivative of that is a line. So the gradient is the tangent to the loss curve at that point. It tells us how the loss is changing at that point with respect to Wi, which is an instance of weight, for example. Now, we want to focus a little bit on eta, which is the value we are subtracting or multiplying the variation of the loss to the weight. The variation of the loss to the weight can be negative or can be positive. And let's take a look at the formula. The new weight is equal to the old weight minus eta times the variation of the loss to the weight. If the variation of the loss to the weight is negative, then we will be increasing the old weight with a value of eta times variation of loss to the weight. While if the variation of the loss to the weight is positive, then we are subtracting, we are reducing the weight, the old weight, okay? So eta decides how fast or how slow we move down the loss curve until we reach the minimum loss, okay? So if eta is too large, the updates overshoots the minimum and cross to the other side. And then the loss oscillates a lot or diverges. The training becomes unstable. While if eta is too small, then the training becomes extremely slow. The model may get stuck in a poor local minimum, and the gradients effectively vanish over time. Our ultimate goal here is for the tangent to the curve to have a slope of 0 parallel to the x-axis. This is really the minimum of the loss function. So this is our goal. On this slide, we present how the slope to the curve changes on two separate points, where x is equal to minus 1.45 and where x is equal to minus 0.35. Now let's remember that x here is the variable to the function, and it can be the weight or can be the bias, which is the parameter, okay? So for the point x, where it's equal to minus 1.45, the value y is 2.10, and this is represented by the dot, the red dot on the left-hand side of the screen. And here at this particular point, the slope is equal to minus 2.9. Now remember, in the previous slide, our goal was to achieve a slope of 0. Minus 2.9 is away from 0. Okay, we want to reduce this difference between the slope and 0. So as x moves closer to the origin of the axis, which is 0, 0, so when x changes from minus 1.45 to minus 0.35, the value of y becomes 0.12 and the slope becomes minus 0.7. Now obviously minus 0.7 is closer to 0 than minus 2.9. What this tells us is that we are moving in the right direction. We are descending the gradient properly, negatively, toward the minimum loss. This slide is a continuation of the previous slide. So let's say we move x even closer to the origin and we position it exactly at the origin. So x is equal to 0, weight is equal to 0, okay? So when x is equal to 0, then y is equal to 0. And the slope here in this case is 0. This is the perfect condition for us. It means the loss is at a minimum, meaning the model is predicting properly and the loss between the predicted value and the actual label is 0. It means the model is working very well, at least for the dataset batch that we are using for training. Now, if we move the value of x away from 0, if we increase it from 0 to 0.35, then we see that the slope becomes 0.7. So here we are diverging away from the minimum loss. We are increasing the loss, which means we overshoot the system, and the model now is causing even more errors than previously. The perfect condition is for the slope to be 0, and now we missed the 0 and we have a positive slope. It means we are moving away from the minimum loss. Before we dive into the back propagation, it's important to explain what the chain rule is, because the chain rule is used extensively in the back propagation. So let's talk about the chain rule first, which is important to understand because it's very essential for the back propagation. The chain rule is a rule in calculus. It's used to compute the derivative of composite function. So a function inside another function. Let's think about it as a function gx that operates on input x, and then another function f which operates on the function gx, which is also a function of x. So we end up with f of g of x. A small change in x will imply a change in gx, and a change in gx will imply a change in f of gx. So whether the change is small or large in x, there is always a change in the final output f of g of x. The chain rule measures how those changes propagate through the chain. First, when x changes, how gx changes, and then how f of g of x changes. So the chain rule is the mathematical foundation of backpropagation in neural networks. Output is like f3 of f2 of f1 of x, and it can be even more nested than that. It may be many functions are concatenated within each other. So it can be nested functions. The chain rule allows us to compute the variation of the loss with respect to the weight, and we talked about this in the previous slides. How do we use the chain rule to compute the variation of the loss with the weight? We do that by multiplying the derivatives layer by layer, and we will see this in a second. Let's first take a look. Let's consider a real mathematical example. So the function y equal f of x is equal to 3x plus 2 to the power 5. This is a composition function as follows. So we have the 3x plus 2. Let's say it's equal to u. In this case, y is equal to u to the power 5. The derivative of y with respect to x, in this case, is equal to 5 times 3x plus 2 to the power 4 multiplied by the derivative of u, which is 3x plus 2. So we end up with 5 times 3x plus 2 to the power 4 times 3, which is equal to 15 times 3x plus 2 to the power 4. Now let's take a look at the backpropagation in neural networks and how it is used to fine-tune the weights and bias. Backpropagation is the process used to fine-tune the model's parameters, its weights and biases after forward propagation. During training, these parameters produce a predicted output, y hat, which often differs from the true label in the training data. This difference generates an error measured by the loss function, indicating that the model's predictions are not yet accurate and that the parameters need adjustment. This relationship is illustrated in a diagram below. Because the weights and biases are the knobs we adjust to reduce loss and improve prediction accuracy, we must determine how much each weight contributed to the error. Mathematically, this means computing the partial derivative dl over dwi. However, the loss depends on the predicted value y hat, and y hat itself depends on the activation function, rectified linear function z, or real u z. Meanwhile, z depends on the weights. Therefore, calculating dl over dwi requires applying the chain rule, since each quantity is a variable, is a function of another. Backpropagation uses these chain derivatives to update the weights and biases gradually, reducing loss and improving the model's predictions. What we have on this slide is the math of what I just explained in the previous slide, specifically the chain rule and how it is used to calculate delta L divided by delta W. Let us assume that in our model we are using only two weights, W1 and W2, that multiply the inputs x1 and x2 respectively, resulting in z equal W1x1 plus W2x2 plus b. This is shown in the diagram below. We see the summation function adding W1x1 and W2x2 and adding a bias to the result. This is the linear transformation we explained earlier. Obviously, it is dependent on W1, W2, and B. In order to calculate how each weight affected the loss, i.e. delta L divided by delta W1 and delta L divided by delta W2, i.e. the rate of change of loss with respect to the weights W1 and W2, let's take a look at the chain rule formula first. Okay, it is shown at the top of the screen. So delta L divided by delta Wi is equal to delta L divided by delta Y hat. Delta Y hat divided by delta Z multiplied here, there is a multiplication. And finally multiplying the third term, which is delta Z divided by delta Wi. So Wi meaning W1 or W2, or it can be B actually, the bias, okay? The formula tells us that we need to calculate first delta L divided by delta Y hat, and then we need to calculate delta Y hat divided by delta Z, and delta Z divided by delta W1 and delta W2 and delta B, which is the bias. Let's calculate the first term. Delta L divided by delta Y hat. Okay, so delta L divided by delta Y hat is actually how much the prediction affected the loss. Okay, so when you see delta L divided by delta Y hat, what we are talking about here is how much the prediction or the predicted value affected the loss. Okay, now let's remember the loss function. L is equal to 1/2 Y hat minus Y to the power 2. Its derivative with respect to Y hat is simply Y hat minus Y. If you're not sure how this is calculated, please read about derivation and how to calculate derivatives. Let us calculate the second term now. Delta Y hat divided by delta Z. This is equal to 1 if Z is positive, and it's equal to 0 if Z is negative or equal to 0. In a way, this is acting like a binary switch. Finally, let us calculate delta Z divided by delta W1, delta Z divided by delta W2, and delta Z divided by B. So here what we are calculating, okay, is the derivation of Z with respect to 1, the derivative of Z with respect to W2, and the derivative of Z with respect to B. Those derivatives are equal to x1, x2, and 1 respectively. Nothing strange here. This is pure math derivation calculation. All we need to do now is to plug these three results into the chain rule equation to calculate the final gradient formulas with respect to the weights W1, W2, and bias B. I hope this is clear. For those of you who like to practice with Python and implement this in Python, of course you can do that. However, there are libraries available such as TensorFlow and others in Python to do the calculation for us. The alternative would be to code line by line all these operations, and this will be a very tedious task, especially when the number of neurons and layers increase as it gets harder and harder to calculate the weights and biases through programming every step. So I hope you enjoyed the video, and if you have any comments, please feel free to write your comments in the comment section below.